Have you ever really stopped to think about how a tiny bit of gasoline can move a 2-ton car? Or how that sandwich you had for lunch is literally fueling your body right now? Well, that's all thermochemistry. It's the science that's hiding in plain sight, pulling the strings on the flow of heat and energy in every single chemical reaction. But here's the big question, right? How can that be? Why is it that lighting a campfire gives off this huge, cozy wave of heat, but cracking one of those instant cold packs makes it feel shockingly icy? It seems like some reactions are giving away energy, while others are just stealing it from everything around them. And figuring that out is exactly what we're going to do. So here's our game plan. First, we're going to get on the same page with the basic language of energy. Then, we'll see how chemists cleverly split the universe in two to track where it all goes. After that, we'll look at heat flowing in and out of reactions, figure out how we actually measure all this stuff, and finally, we'll see how it all plays out in your own kitchen. Let's jump in. Okay, first step, the language of energy. Before we can really dig in, we need to make sure we're all speaking the same language. Let's lock down a few of these key ideas. It all boils down to this one simple definition. Energy is just the capacity to do work or to transfer heat. That's it. Pretty much everything that happens anywhere is because of energy moving around. But what's the real difference between work and heat? Let's break it down. Think of heat, which chemists call Q, as chaotic, disorganized energy. It's the random vibration and movement of atoms that makes things feel hot or cold. Work, or W, is much more orderly. It's focused energy that actually moves an object, like the gas in an engine pushing a piston, or here, a cork flying out of a bottle. And all that energy, whether it's doing work or transferring heat, falls into one of two main buckets. You've got kinetic energy, which is the energy of motion. If it's moving, it has kinetic energy. Simple as that. Then you have potential energy, which is stored energy. You can think of it as energy that's just waiting to be released. Now, for a chemist, the most important kind of potential energy is electrostatic. Opposites attract, right? Well, that attraction is a form of stored energy. When a positive ion and a negative ion get closer together, they're like a ball rolling downhill. They're moving to a lower, more stable energy state, and they release that stored potential energy as they do. And that brings us to what I think is the golden rule of thermochemistry. If you get this one idea, everything else just clicks into place. Forming chemical bonds releases energy, and breaking them costs energy. I know, it feels totally backwards. But think about two magnets snapping together. As they click into that stable position, they release energy. To pull them apart again, you have to put energy in. It's the exact same idea with atoms. All right, section 2, a universe of two parts. Now that we've got the lingo down, we need a way to keep track of all this energy. We need to know where it's coming from and where it's going. So to do this, chemists came up with a really clever trick. They just divide the entire universe into two parts. First, there's the system. That's the one thing we're actually interested in, like the chemicals reacting in a beaker. And then there's the surroundings, which is literally everything else. The beaker itself, the table, you, the air in the room, you get the idea? And these systems can interact with the surroundings in basically three ways. You've got an open system, like a cup of coffee, which lets heat escape and lets you, drink it. Then there's a closed system, like a sealed bottle of water. It can get warm or cold, but the water stays put. And finally, you have an isolated system, like a perfect thermos, which in theory exchanges nothing at all. And all of this is built on one unshakable law, the first law of thermodynamics. It's the ultimate rule of the universe. It says you can't create energy out of thin air, and you can't make it disappear. All you can do is change its form, from the potential energy in a chemical bond, say, to the kinetic energy of a flying cork. Okay, on to section 3, heat in, heat out. Now we get to use our new framework, the system and the surroundings, to finally start classifying reactions based on which way the heat is actually flowing. So any system you can think of has some amount of energy packed inside it, all the kinetic and potential energies of its molecules added together. We call this its internal energy, or E. Now we can't really measure the total E, but we can absolutely measure its change. And that change, which we call delta E, is really just an energy accounting equation. It's the heat, Q, that flows in or out, plus the work, W, that is done. Now, since most chemistry happens out in the open, we have a handy shortcut called enthalpy, or H. Think of it as the heat content of a system, and the sign of its change, delta H, tells you everything you need to know. If delta H is positive, the reaction is endothermic. The system is pulling heat from the surroundings from your hand, which is why it feels cold. If delta H is negative, it's exothermic. The system is dumping heat into the surroundings, making everything feel hot. So that brings us to section 4, measuring and calculating energy. It's one thing to talk about heat flowing, but how do we actually, measure it? Let's take a look at the chemist's toolkit. The most direct method is called calorimetry, and the idea behind it is just beautiful. You take your system, the reaction, and you run it inside an insulated container of water, which is your surroundings. You just measure how much the water's temperature changes. From that, you can calculate precisely how much heat the water soaked up. And thanks to that first law, any heat the water gained must be the exact same amount of heat the reaction lost. Simple, right? But you can't always stick a reaction in a calorimeter. So chemists have 3 really clever ways to calculate the energy change on paper. First, Hess's law says the path doesn't matter, the total energy change is the same whether a reaction happens in 1 big step or 5 little ones. Second, we can use tables of pre-measured values called enthalpies of formation and just do a products minus reactants calculation. And third, we can go right back to our golden rule and add up the energy it costs to break all the old bonds, then subtract the energy we get back from forming all the new ones. And for our last section, let's take all of this out of the lab, because this stuff isn't just theory. Thermochemistry is literally what powers our lives, and you can see it right in your kitchen. When we talk about energy from food or from gasoline, what we're really talking about is something called fuel value. It's a very simple measure. How much energy do you get when you completely burn 1 gram of something? And this is exactly why nutrition labels are so important. Check this out. Carbohydrates and proteins give you about 17 kilojoules of energy for every gram. But fats, they give you a whopping 38 kilojoules per gram. That's more than double the energy. It's not magic, it's just thermochemistry. The specific chemical bonds in fats are just structured to hold way more potential energy. And what's true for your food is true for our whole planet. Our society runs on the massive exothermic combustion of fossil fuels, but we also use other energy conversions. Nuclear power taps into the potential energy locked in an atom's nucleus. Solar power converts the energy in light, and wind power captures the kinetic energy of moving air. See, it all comes back to the same core ideas. So when you boil it all down, what's the big takeaway? Thermochemistry is really just the science of energy accounting. It lets us track where the energy goes during a chemical reaction. It's all built on that fundamental first law, and it gives us the tools we need to measure, calculate, and even predict the flow of heat that really does run the world. But all of this leaves us with one final and I think fascinating question. We now know how to figure out if a reaction will be hot or cold if it happens. But how do we know if it's going to happen at all without a push? Well, that's a whole other story and maybe one for our next explainer. Thanks for watching.